Okay, so this is problem number 1 on the 2.3 homework. And let's just remember what exponential growth model means. Exponential growth model just means that we continue to multiply by the same multiplier all the time. So my initial population is 12 in this particular example. So I know P0 is 12. How do I get to the population at time 1? Well, we take 12 and we multiply it by some multiplier. How do I get to the population at time 2? We take 12. This gets us, the first application of the multiplier gets us to time 1, and then we're going to multiply again by that same multiplier, etc. We just have to figure out what that multiplier is. Every time we move forward, we're multiplying by the same multiplier. So for population at time 3, we're going to multiply by the same multiplier a third time. We keep multiplying over and over again. That's what exponential growth is. Now, what is the multiplier? Well, just realize that if the multiplier happened to be 1, there would be no change. So for example, if I did 12 times 1, that's just 12. If I did 12 times 1 again, it's still 12, no change. So a multiplier of 1 means no change. If we want the population to grow, we have to multiply by something above 1. Okay, so the growth rate tells you how much above 1 your multiplier is. Okay, so the 0.20 is the amount above 1.0, because if you multiply by 1.0, there's no change. Okay, so in this case, I'm going to have that my multiplier, let me change colors for you here a little bit. There we go. So now my multiplier is going to equal 1.0 plus the rate. The rate is the amount above 1. So 1.0 plus 0.20, okay, of course, gives me 1.20 in this case. So my multiplier here is 1.20. I'm growing by 20% each time period because I'm 20% above 1. Okay, the 0.20 is really 20%. Now, of course, we can also write this with exponents, etc. So if I want to be fancy and write it with exponents, I can say, hey, this is really 12 times a single copy of 1.20. Okay, so 1.20 to the 1. This is really 12 times 2 copies of 1.20. So I could write that as 1.20 to the power 2. In fact, I'll just put this in a parentheses just to let it, so it's easier to see visually. Here I'm going to have 12 times 3 copies of 1.20. Remember, when you multiply by a number by itself over and over again, like 1.20 times 1.20 times 1.20, that's an exponent. We're multiplying over and over again by the same thing. Okay, so in this case, they just want to know what P2 is. Okay, so I already know. I just popped that in my calculator. Okay, so in my particular example, I would get 12 times 1.20 times 1.20. On my calculator, I'm getting 17.28 in my case. Okay, if they ask me for P, suppose they ask me for like P10. Well, I could write it out, but I'd have to write out 10 copies of the 1.20. That kind of gets a little bit annoying, but I can do it with exponents a lot easier. 10 copies of 1.20 all multiplying each other would be 1.20 to the 10, etc. Okay, so we could answer any kind of question like this. All right, let's go on to the second problem. Okay, so here is problem number 2. And again, exponential growth, so that's a constant multiplier. We're always multiplying over and over again by the same thing. So as soon as I see exponential growth, I can already start writing, okay, what is my P0? In my case, it's 13. What's my P1? This will be 13 times some multiplier. What's P2? It's going to be 13, because that's my initial, times some multiplier times the same multiplier again, etc. Now, are they telling me what the multiplier is? So remember, what is a rate? When they say a growth rate, that's the amount above 1.0. Because as we said before, if your multiplier is 1.0, there's no change. If you keep multiplying by 1s, there's no change. There's no growth. So the growth rate is how much above 1.0 we are. Okay? So in this case, I'm going to have 1.0 plus 0.04 gives me 1.04. That's my multiplier. Okay? So I just pop that 1.04 into my little chart here, and I'm all set. Okay? Now, of course, I can do this more cleanly or more quickly with exponents, if I like. Okay, so this is just 13. This is 13 times 1 copy of 1.04, so that's exponent 1. This is 13 times 2 copies of 1.04, so that's exponent 2, etc. Okay, and we can just keep doing that. So in this case, they want to know what P13 is. So if I go way down here to P13, I could, of course, Now the 13, this 13 has no relation to this 13. That's just an accident. Okay, so don't get confused there. Okay, there's no, it's just accidental that the numbers matched. But my P13 is going to be my initial value, whatever it was, times 13 copies of 1.04. So I could write them all out if I felt like it, right? I need 13 copies of this because I want P13. Not because the initial value is 13, that's irrelevant. It's because I want the 13th time value. So I need 13 copies. Okay, now how do I do 13 copies? I could write it all out, or I could just say my initial value, right? That's my initial population, my P0, times my growth factor, or my multiplier, and then power of whatever the copies are, the number of copies, the number of each copy of the multiplier. This is copy 1, copy 2, etc. Each copy of the multiplier is moving ahead by 1 time unit. So if I want to move ahead by 13 time units, I'm going to go power 13 there. But again, this 13, don't be confused. It's unfortunate that they matched in this problem. This 13 is because of wanting 13, moving forward by 13 time units. Okay? Just like this is 2, right? Because I'm moving ahead by 2 time units. Okay? So in fact, just to make you less confused here, suppose they ask me for P12. If they ask me for P12, well, P12 would be 13, because that's my initial, times 12 copies of 1.04. I would need 12 copies of this. So that's going to be 13 times 1.04 to the 12. Now they say, what is it? They say to find an explicit formula for Pn. So have I already done that? The answer is yes, I basically have, because this can be your n. N is the number of time periods. So essentially what I found is that after n time periods, I'm going to have what? I'm going to have 13 times, this is the number each. If n is 2, for example, I have 2 copies of the 1.04. I indicate that with an exponent. If n is 12, I'll have 12 copies of the 1.04. Okay, so the n is 12. So what I'm saying is, would take my initial value, which is 13, times the factor, or multiplier, which is 1 plus the growth rate, and then put it to the power of whatever the time units are. So how many times have I moved forward? And so in this case, the n is the number of times we've moved forward. Number of times we have moved forward in time. Okay, and so every time I move forward, I'm multiplying by a higher copy. I'm adding 1 more copy of the 1.04. That means my exponent keeps going up. If I go move forward n times, I'm going to have n copies of the 1.04. So this would be my explicit formula right here, when they talk about an explicit formula. Okay? N is the number of times we move forward, and that's how many times I multiply by my growth, my multiplier or factor. Okay? And so now can I use that to get P12? Yeah, we already have been using it. We just didn't sort of put the n in there, but we've been using the same idea. Okay? All right, so let's go on to problem 3. Actually, before we go to problem 3, let me just remind you of how to analyze, like how would I compute this on a calculator? So if I'm on a calculator, exponents are, you use a little wedge character. So on my calculator, I would type 13 and then times, or parentheses, either way, 1.04, and then I'd use that little wedge character and then put the 12, that sort of thing. Okay? That little wedge is to indicate exponents. All right, so let's go on. Okay, so we're on problem number 3 here. Whoops. Okay, that's a little better. I was paging back through the pictures here. Okay, so we're on problem 3. And again, as soon as they say exponential growth model, I immediately can start writing down, okay, I'm going to start with P0, and they're giving me a P0. And then how do I move to P1? Because of exponential growth, you're going to take your initial value times your growth multiplier. Okay, some books call it a growth factor. If you look online, you'll see it called a factor a lot. Growth multiplier or growth factor. If I go to P2, it's going to be my initial, and then we move ahead to period 1, and then I'm moving ahead again to period 2. P3 would be same idea. Initial value, period 1, period 2, now I'm at period 3. Okay, or population at time 3. So now, do I know what the multiplier is? Well, in this particular problem, they're not telling me the multiplier. If they would give me the growth rate, like if they said, oh, the growth rate is 0.2, then my multiplier would be 1.0 plus the 0.2 or 1.2. Okay, but they're not telling me that. They want me to deduce what the multiplier is because they're going to give me the value of one of these populations. And in fact, they're giving me the value of the population at time 1. So they're saying the result at time 1 is equal to 253 in my case. Okay, so that means I just have to solve this. I don't know what the factor is. I don't know what the multiplier is. I'll just call it m for multiplier. Okay, so I just have the equation that 214 times a single copy of the multiplier gives me 253. Why is it a single copy of the multiplier? Because they're giving me the P1. If they would have given me P3, there would have been 3 copies of the multiplier, etc. Okay? So what do we do here? Well, we just solve this for m. How do I solve this for m? It should be pretty easy, right? I'm just going to divide both sides by, let's kind of just remember our basic algebra. I can divide away the 214 on both sides, right? So I end up with m, because the 214s will cancel. M is what? This, right? Which in my case is 1.182, okay? So I know that that multiplier is 1.182. Now, how does that help me answer the problem? Well, how do I get from one time period to the next? So let's kind of fill this chart in. Now that I know that it's 1.182, let's go ahead and fill that in. Okay, so I'm going to have 1.182 in the box each time. Where did I get that from? From this, solving this equation. So what's going on is each time we move forward by one time period, what's happening? To move forward, let's do a different color here, I guess. Let's try, I don't know, we'll go, I guess I've been using orange. I don't know, we'll go with light green. Okay, so each time I move forward, how did I move from P0 to P1? I multiplied by an additional copy of that multiplier. How did I get from P1 to P2? Okay, this is already P1. How did I get to population at time 2? I multiply again. Every time you move forward, you multiply by that multiplier. This is all P2. How did I get to P3? I multiply by an extra copy of the multiplier. Every time I move forward, I multiply by an extra copy. Okay, so to get to population at time n, it would be basically I'd have 214 times whatever I had before. I'm going to have whatever my number of multipliers was before, and then I'm going to add a new copy of the multiplier. Okay, I'm going to multiply in one more copy. Okay, so this much here would be population at time n minus 1. Whoops, I'm kind of running out of space at the bottom of the page here. Population at time n minus 1, and then I'm going to add in or multiply in one more copy of the multiplier. So what we're getting at is no matter what time you're at, like if I'm at P2 and I want to get to P3, I just multiply in by an extra copy of the multiplier. Okay, so the whole idea is to get from the population at time n, to reach the population at time n, I take the population at time n minus 1, and I multiply by the multiplier. Okay, so that's my multiplier. If you multiply by the multiplier, it takes your population at the previous time and gives you the population at the next time. Okay, we've been putting the multiplier at the end when we build our little tables, but we can also write the multiplier at the beginning. It just kind of looks a little prettier that way. Okay, so in my case, I'd have a 1.182 here. If I multiply by 1.182, I'll take the previous times population and get to the next times population. Okay, and there we go. All right, let's go to number 4. Okay, so here's problem number 4. And in this case, it's similar to the previous example, but they're giving me a different future value of the population. Okay, they're giving me, we're starting off at a P0 and then we're ending at a P5. But as soon as I see exponential growth model, I can immediately write down what I always do, which is I have a population at time 0, which they're telling me is 3050. How do I get to the population at time 1? It's going to be the initial population, and then I multiply by the one copy of the multiplier. To get to P2, same thing, just multiply by another copy of the multiplier. Every time you move forward, you're multiplying. That's what exponential growth is. You keep multiplying by the same number over and over again. You start with a certain value, and you just keep multiplying. Okay, P4, and I'm going to go to P5 because they're asking me about P5. So there's P4, 4 copies of the multiplier. P5 is going to be 5 copies, right? So it's a little annoying to write, but, you know, there's... It's not the worst thing in the world. Okay, there's 5 copies of the multiplier. Okay, there's P5. Now, do I know what the multiplier is? No, they're not telling me. But they are giving me the P5 value, right? They're telling me that the P5 happens to be 3,615, right? In my case. So immediately I know that, so if I just kind of extract this out, this little relationship right here, I see that 3050 times this multiplier, I'll just call it M, right? I put 5 M's in a row, all being multiplied. M, 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 all being multiplied. Is that 5 of them? Let's see, 1, 2, 3, 4. Yep, equals 3615. Now, can I write this more compactly? Sure, I can put, when you multiply by the same number over and over again, that's exponents. That's really m to the 5th. So I have 3050 times m to the 5th is 3615. Now, how do I get the m? Okay, algebraically, if you're trying to solve for a variable, you first move everything away. So I have to get rid of the 3050. The 3050 is multiplying the m, right? So how do I get rid of multiplication? I'm going to divide on both sides, okay? And then, so now I've got the equation m to the 5th is equal to my 3615 over my 3050, and of course I could just punch that up on a calculator, get a decimal for it, but it might be a long decimal, so I'm just going to leave it like that for now. And then, how do I get rid of a 5th power? That's a little tricky for students if you don't remember your rules of exponents. The way to get rid of a 5th power is to use a 1/5 power. Okay, so I'm going to write this as, let me just rewrite what I had. So I have m to the 5th equals 3615 over 3050. And now I want to get rid of the 5th power, so I'm going to use a 1/5 power on both sides. As long as we do the same thing to both sides, it's legal, right? It's mathematically correct. 1/5 power, 1/5 power. Why does this work? Because when you put a power on a power, you multiply the powers. When you put an exponent onto an exponent, you multiply the exponents. So what am I ending up with? I'm ending up with m to the 5 times 1/5. 5 times 1/5 is 1. Okay, which is just m to the 1. So this is really m to the 1, which is just m. Anything to the 1 is just itself. So by putting a power 1/5 onto the power 5, we end up with the power 1, which just gives me m by itself. So I have m is this quantity. Okay, so I just put this on my calculator, right? So in my calculator, I'm going to do this. I'm going to say parentheses on my calculator, because you want to make sure you're applying the power to the entire fraction. 3615 divide 3050, then put your character, then a parentheses again, because I want to make sure that the calculator understands that the 1 and the 5 are both part of my exponent. Okay, so I would put that in my calculator. Okay, and I should get, if you round off to 3 decimal places, I should get 1.035 in this case, in my particular example. So that's my m. That's my multiplier. Okay? So that means this would be 1.035, etc. We could check it if you want. Just if you want to check it, just take your 30, take whatever your initial population is, and just multiply by, in my case, 5 copies of the 1.035, like multiply by 5 copies of it. You should get this number. You might be off by a slight, tiny amount because this is a round off. I've rounded off my m. If I use more decimal places, it would work out exact. Okay? But as long as you're super close, you should be good. Okay? And that's it. That's how we're doing. So the idea is they're giving me a later time value, which means this time value, 3615, incorporates the initial, and then since it's P5, it incorporates 5 copies of that multiplier. So power 5. So that's why I ended up with m to the 3050 times m to the 5th equals my ending value. And I have to get rid of the 3050 by dividing it. And then I have to get rid of the 5th power, and the way to get rid of 5th power is use 1/5 power. Because power times power on a power you multiply, 1/5 times the 5 gives you a power 1. Okay, and there you go. Fun, right? Let me check that. Yeah, I just Googled it. That is fun. Google says that's fun. Okay, it's official. Whoops, I forgot to just help you finish up the problem here. My bad. So what we found that the m in the previous problem was 1.035. So just to remind ourselves, P0 would be my initial population. My P1 would be what? My initial population times that multiplier. that we located or figured out using some algebra. So every time we want to move forward, we just multiply by an additional copy of that multiplier, etc., right? And so what we see is if I want to get, for example, from P0 to P1, then P1 might, or let's say we're going from P1 to P2, okay? So in that case, I could think of P2 as like my P population at time n, where time n, the n is 2 in this case. So that's kind of what they're thinking about here. And then the previous time value would be, population at time 1 would be n minus 1. If you take the index or time counter and you subtract 1 from it, you're going 1 period back. So this, if this is my Pn, then this would be my Pn minus 1. So how do you get from Pn n minus 1 to Pn? How do you move forward? You multiply by the multiplier. Okay? So that's kind of what they're getting at here. Each time period is just the multiplier times the previous time period. Okay, so what they're looking for in this box is the multiplier. The multiplier moves you from any particular time period 1 unit back, and it's going to move you forward by 1 unit and get you to that next time period. Okay, so as soon as I figured out my multiplier, which you see it right here is 1.035, that's my answer. Okay, that's kind of what they're getting at in this problem. Good? All right, so now let's move forward. Okay, so here we are on, let's see, this is problem number 5. And so again, as soon as I see my initial population, I'm going to write it down. P0 is 3,000. How do I get to P8? Well, P1 is going to be what? 3,000 times some multiplier. They're not giving me the multiplier. They want me to figure it out. Okay, P2 would be my initial population times the multiplier, and then to move to the next time unit, multiplier again. How would I get to P8? So they're giving me P8. P8 is going to be 8 copies of the multiplier. Well, I don't want to really write out 8 copies, so let's, there's 8 of them. 8 copies. I'm just going to kind of be lazy here, just write 8 copies, and I'm going to use exponents to do my work. Okay, so this is really 3,000 times 1 copy of the multiplier, whatever that multiplier is. This is 3,000 times 2 copies of the multiplier. This is going to be 3,000 times what? 8 copies of the multiplier. And every time you multiply by the same number over and over again, you're raising the exponent. That's what exponents do. They multiply by the same number over and over again. Okay? So that's power 8. Sorry, it's a little scary looking 8 there. And now, do I know what the multiplier is? Well, we can figure it out, right? Because let's just call that multiplier m. So we have a little, so we're filling it in with at least some symbol. So I have m to the 8th. And they're giving me the value, right? They're telling me P8 is this number. So I know that this is 3425. Okay? So how would I figure out what the m is? I need to figure out what that multiplier is, just like before. How do I figure out the multiplier? Well, I need to algebraically get stuff away from the m. How do we get stuff away from the m? First thing I'm going to do is what? I'm going to divide away the 3,000. So I have m to the 8th, these cancel. So I have m to the 8th is 3425 over 3,000. Okay, then what? I need to get rid of 8th power. How do we get rid of 8th power? So I'm just going to rewrite this. I have m to the 8th is 3425 over 3,000. Now what do? I need to get rid of the 8th power, and as we said before, the way to get rid of a power is to use 1 over the power, the reciprocal of the power, because when you multiply the powers, that's just going to become power 1. But make sure to do that on both sides, or it's not, legal. It'll change things. You have to make sure to do the same thing on both sides. So this works because, as we said before, when you place an exponent on an exponent, you multiply. So this is really the exponent 8 times 1/8, which is 1. So I just have m to the 1, right? At this point, I just have m to the 1 is equal to, because 8 times 1/8 is 1. M to the 1 is just m. So here's my quantity. I can do this on a calculator, right? So I can place this on a calculator. So on my calculator, I'm going to do this. I'm going to say 3425 divide 3,000 caret, parentheses again for the exponent to make sure both the 1 and the 8 go into the exponent. Okay? And you'll get a number. Okay? And you should get approximately 1, in my case, 1.017. Okay? So that's my multiplier. So that means to move ahead, in my case, I'd be multiplying by 1.017 every time. Okay? Now, the next question is, they don't want the full, this is the full 1.017. But what they're asking you to do is identify which part of this is the growth part. The growth part is the part above 1. So they just want the part that's above 1. Okay, the part that's above 1 is obviously going to be what? The 0.017 is the part above 1. Okay? So that's the actual growth amount, 1.7% or 0.017. Okay? So that's the part above 1. The 1.017 consists of, if you take the 1.017, it consists of a 1, right? And then the point plus the 0.017. This is what would be called the growth rate R. That's how much above 1 you are. That's how much you're growing by. If you multiply by 1 every time, there's no change. This gives you your actual growth, the part above 1. Okay? And that's what they're looking for here. Pretty cool, huh? All right, so let's go on. Okay, here is problem number 6. And so my initial population was 4,700. So I'm going to call, and this is the first data they're giving me, 2012. So I'm going to call that P0. Okay, so I'm going to say P0 is 4,700 people. Okay, how do I get to P1? Since it's exponential growth, I multiply by a multiplier. Exponential means you multiply. P2 would be 4,700 times the multiplier times the same multiplier again, etc. Okay. In fact, let's remember what the years are. So P0 is for what year? That's 2012, right? This would be 2013, 2014. So how would I get to 2018? They're giving me data for 2018. Okay. Well, how many? Let's see. So 24. I have 2015, 2016, 2017. 2018, right? Each time I'm going to multiply by an extra copy of the multiplier. This is P3, P4, P5, P6. I could have figured out it's P6 because 2018 is 6 years later than 2012, right? So I know there's 6, I'm moving ahead by 6 time units. So I'll just jump right to here. I'm going to have 4,700 times how many copies of the multiplier? 6 copies. How do I know it's 6 copies? Because every time you move forward, at P1, it's 1 copy, right? At P1, it's your initial population times your multiplier to the 1. By P2, it's your initial population times 2 copies of the multiplier, so power 2. By P6, you're going to have 6 copies of the multiplier. 4,700 times 6 copies of the multiplier, okay? So that's my population in 2018, is P6. And they're telling me, actually they want me to figure that out, right? So all I need to figure that out is I need to know what the multiplier is. Are they giving me information about the multiplier? And the answer is they are. Why? Because they're telling me the growth rate was 4%. Now remember, percents need to be made into decimal form before we use them. So let's just remember that 4%, we move the decimal 2 places to the left to make it into a decimal number. So it's going to become 0.04 as a decimal. This is the amount above 1.0 because that's the growth rate. 1.0 means no change, right? So if we're growing, we're going this much above 1.0. So that tells me that my multiplier is what? 1.0 plus the growth rate. Okay, so that means the multiplier is 1.0 plus my 4%. 4% is 0.04. Okay, so that's 1.04. So I just know that I'm multiplying by 1.04. The 0.04 portion tells you how much you're growing. That's your growth. The 1.0 just keeps things the same. Okay, the growth is the part above 1. Right, so I know that I'm all 1.04s here, right? All the way along. So it's easy to figure out. I can just pop that into my calculator to figure out what my population is going to be in 2018. So step 1 in this problem is realize I have to move forward 6 time units. So I'm going to have power 6 on my multiplier. Okay, next thing is I need the multiplier. So in this case, they're telling me the multiplier because when they tell you the growth rate, they're telling you how much above 1.0 your multiplier is. I'm 4% above 1.0. That means 0.04 above the 1.0. Okay? And there you go. Okay, so my multiplier is 1.04. So once I pop that in, I can just compute my result. My result's going to be, in this case, I'm getting 5,947. Okay, in my particular example. That's the number of people. Okay, let's go on. Okay, so problem number 7 here. So in 1983, that's the initial amount that they're giving me, 1,800 people. So we'll call that P0. P0 is 1800. That's for the year 1983. Okay? Now, what happens by 1984? Do we know? Well, P1 is going to be the previous value times what? Times a multiplier. P2, which would be for 1985, would be what? The same value from before, from the previous time period, times the multiplier again. We keep multiplying by the multiplier, etc. Okay, now do I know what the multiplier is? Well, in this case, we're lucky. They're telling us, right? The multiplier is 1.8. We don't have to figure it out. The growth multiplier is 1.8. Okay, which is scary because that means 80% growth. Every time period, you're going to be 80% higher than the previous time period. The amount above 1 is 0.8, which is 80%. So that's kind of scary. Okay, so what's going to happen by, how would I get to the year 2001? Okay, well, the year 2001, let me change colors here a little bit. The year 2001 is how many years? Well, I'm going to take 2001, take away 1983, I get what, 18? So that means I'm going to go all the way down to year 18. So P18 should be the year 2001, right? And what's that going to be? How would I write that out? You should be a pro at this by now. I'm just going to have how many copies of that 1.8? How many copies? 18 copies. How do you do that? I could sit there and multiply by 1.8 18 times on my calculator, or I can kind of get clever and just use exponents, right? 1800 times 1.8 to what power? Again, it's kind of unusual that everything had, it's unfortunate that they're asking you about a year 18 and there's an 1800 and a 1.8. That's all coincidence, okay? The key is that the year 2001 corresponds to the 18th time period, so that's your exponent. The exponent tells you the number of time periods that you're moving forward. Okay, so let me go ahead and do this on my calculator. Hang on a second. Okay, so I'm getting 70823534.54. Okay, and round to the nearest whole number, so that means I'd round up. So it'd be 70823535 to round to the nearest whole number. And I'll put some commas in there. So 70,823,535, which is a huge number of people. So it's a good thing it didn't go unchecked. At least there was some, medical intervention back then to slow it down. Okay. All right. So let's go on to problem 8. Okay. Here's problem number 8. And problem 8's a little bit tricky because we're decreasing, not increasing. That means we're going to subtract away from 1.0. Decreasing means you go below 1.0. 1.0 means no change. So 4% is as a decimal. Remember how to change this to a decimal? 4.0% to move to a decimal, we go to the left 2 places. So this becomes 0.04 as a decimal. But it's 0.04 below 1.0. Why is it below? Because we're decreasing. We're decreasing the money. Okay, so I'm going to take 1.0 minus 0.04, not plus. I get 0.96. So in other words, if we lose 4% every year, that means we're keeping 96%. So the money's worth 4% less every year, but that means it's worth 96% as much as it used to be worth. Okay, less than 100%. So this is my multiplier, right? This is what's called the growth rate. The rate in this case is negative, and this is my multiplier, or some books would call it a factor if you look online. Okay, and so we just use our multiplier. Same thing as always, right? Population at time 0 is actually a value of money at time 0. Okay, would be $100. And then if I move forward by 9 years, so P1, or value of the money in year 1, would be 100 times what? Factor, or multiplier, right? Population at time 2, or value of the money at time 2, same principle, multiplier. Multiplier, in this case my multiplier is less than 1 because I'm decreasing. Okay, how would I get to, you guys could figure it out, right? How would I get to the time 9? Same thing, right? I'm just going to have 9 copies. I don't want to write out all 9 copies, but we're going to have 9 copies. And you should, by this point, be a pro and should be able to do this with an exponent. Okay? So in my case, I'm getting 69.25 when I work this out to the nearest 2 decimal places. Okay? And there you go. You should be able to do this with an exponent. I'm not going to show you. You should be able to do this by now. I might do it with an exponent. You should be able to do that. All right, let's go on to our last problem. Okay, so problem number 9 about the wolves. As soon as I see exponential, okay, population grows exponentially, that means I can start my process. Start with P0, and I know how to get to P1. You multiply by a multiplier. Now, they're not telling me what the multiplier is. I'm going to have to figure it out. But we know how to figure it out now, okay? We just kind of keep growing our population until we get to a point where they give us some data, okay? They're giving me a data after 5 years in my case. So I want to go all the way to P5. Okay, so let's use exponents here. This is going to be what? This is 210 times, let's call this m for the multiplier. So this is going to be 210 times m to the 1. At population of time 2 would be 210 times m to the 2. How would I get to the population in year 5? I'm going to have 5 copies of the m, right? M, 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 M. That's a lot of m's. That's 210 times what? M to the 5th, right? Are they giving me a value for that? Yes, they are, right? They're saying that that is 310. So we should be able to, at this point, I'm going to leave you to figure out what the m is. Use the principles that we talked about earlier in the video to figure out the m. So you can deduce what the m is. So you want to find the m, solve for m. And remember, to solve for m, it's 2 steps. First, you get rid of the 210, and then you get rid of the 5th power. If you're not sure how to do that, just back up on the video. Okay, but I'll leave that up to you. So you're going to solve for m. And once you have your m, what do? Once we have my m, then we know how to move forward, right? So how would I get to 14 years? They're asking me for 14 years, right? In my case. So what would P14 be? P14 is going to be 210 times a whole bunch of m's. How many m's? 14 copies of the m, right? So once I know what the m is, I can now just move forward to the 14th year. It's just going to be 210 times m to the 14th power. Okay, because each time you move forward, you're multiplying by another copy of m. That means the power is going up by 1 each time. Okay, so 14th year, 14 copies of the m, power 14 on the m. So once I know the m, I can then plug it in here and get my result. Okay, and round to the nearest whole number. And to the nearest whole number with my data, you should get 625 with this data. Okay, just if you want to practice. Okay, and that's it. I think that's our last problem. That was fun, right? Let me check it. Yep, Google says that's fun. I just checked it. And there we go.